All right, let's use calculus to discuss the end behavior of a few functions. So we've got four functions here. The first one is a polynomial. And then these three down here are rational functions. Now, if you remember graphing polynomials and rational functions from algebra, for polynomials, you know that the end behavior is dictated by the leading term of a polynomial, right? This is the most powerful term, right? This x to the fifth is going to quickly outgrow the x squared. And it's obviously going to quickly outgrow the 11 because 11 never grows, right? This function, as we look at larger and larger x values, is going to be impacted more and more heavily by the leading term, the minus 2x to the fifth. And of course, there are four subcases, right? You can either be an even degree with a positive coefficient out front or a negative coefficient out front, or you can be an odd degree with a positive coefficient out front and a negative coefficient out front, right? You knew from algebra that these are the only four subcases for the end behaviors of polynomials, and it's completely dictated by the leading term, right? The sign right there and the degree, whether or not it's even or odd. Let's use calculus to understand why. So first, before we jump into any of this, we're going to use the same trick over and over again. So let's discuss what trick this is. If you take the limit of a product, let's say f of x and g of x. Well, f of x and g of x might play together. They might interplay in such a way that there's some cancellation and you might get something surprising. For instance, think about x times 1 over x. Now, just because x is going to infinity doesn't mean that this whole term is going to go to infinity, right? Because we can simplify first. X times 1 over x just gives you a 1. So the limit as x goes to infinity of 1 is just a 1 right there. So just because one of the terms in the products goes to infinity doesn't mean that the entire product is going to go to infinity, right? In fact, it's because even though this goes to infinity, this term right there drops down to 0, right? So they kind of canceled each other out. But what we're going to use is that if you have a product, f times g, and you can show that one of them is bounded, meaning that it's not going to drop down to 0 and cancel out the growth of the first function, or it's not going to go up to infinity and cancel out the decay of the first function, right? If I can show that one of the functions is bounded, it's not going to go to infinity, it's not going to go to 0, then the behavior is going to be dictated by the non-bounded part. So we're going to use this idea over and over again. In fact, for all four of these functions. Let's think about the first one. The limit as x goes to infinity of minus 2x to the fifth plus 7x squared plus 11. And we'll talk about whether or not x is going to positive infinity or negative infinity. The work is going to be mostly similar. And we are going to employ the same trick over and over again. I'm going to factor out the most powerful term. So I'm going to factor out the leading term of the polynomial. So if I take a 2x to the fifth away from that term, I'm left with a 1. If I take it away from the second term, I'm left with a 7 over a 2x cubed. And because I removed a negative, this sign, oops, that sign right there is now positive. Oh, wait, sorry, it is a negative. In fact, I have to double check myself on all of these. If I take a negative 2x fifth away, right, if I gave this term right back to this, the 2's would cancel, the negative and the negative would give me a positive. I'm left with a 7 and 2x's on top. That's right. And then what do we've got here? We've got a minus 11 over 2x to the fifth. So I've written my limit, or I've written my function as a product of two things. And let's think. As x goes to infinity, what's going to happen to this term? Well, as x gets larger and larger, whether or not it's positive or negative. But as x gets larger and larger in magnitude, this denominator is going to get larger and larger, which means this fraction is going to get smaller and smaller. It's going to drop down to 0. Same thing here. This fraction is going to get smaller and smaller and drop down to 0. So this whole term, 1 minus 0 minus 0, that's just going to approach the value of 1. So as x gets larger and larger, that term approaches the value of 1, so it's bounded. It's not going to 0, it's not going to positive infinity or negative infinity. It's approaching the value of 1, so the limit is going to be dictated by what's happening to the minus 2x to the 5th term. And what happens as we send x away from the origin of minus 2x to the 5th? So if I think as x becomes more and more negative, right, as it becomes larger in the negative direction, then this is going to approach the value of positive infinity. Right? As these x values get larger and larger, but they're negative, the negative is going to cancel with that negative, and the whole term, minus 2x to the 5th, is going to approach the value positive infinity. So this would be x is going to minus infinity. As x approaches positive infinity, as it gets larger and larger in the positive direction, that x to the 5th is going to get larger and larger, and that negative right there is going to make it negative. So this is going to approach minus infinity. So the calculus tells you exactly what you learned in your algebra class. As I go in this direction, my function drops down to minus infinity. As I go in this direction, my function goes up to positive infinity. All right, let's do this again for the 3 rational functions. All right, my second function is a rational function where I have a third degree being divided by another third degree. So remember from algebra, the end behavior of rational functions, if you're going to have a horizontal asymptote, if your degree on top is the same as the degree on bottom, then both numerator and denominator are going to grow roughly about the same pace. So our behavior is going to be dictated by the leading coefficients. So I should be looking for a horizontal asymptote at the value of 2/5. And let's use calculus to show this. If I look at the limit as x goes to infinity, and again, we'll think about this as going to positive infinity or minus infinity as we go through the work. So in fact, maybe I'll say plus or minus infinity. 2x cubed plus 2x over 5x cubed minus 7. We'll do the same trick and pull out the most powerful term from top and bottom. So my numerator can be rewritten as 2x cubed times 1 plus 1 over x squared. My denominator can be rewritten as 5x cubed times 1 minus 7 over 5x cubed. Now, for the same reason, as x gets larger and larger, either negatively or positively, that term is going to, approach 1, right? This term approaches 0, so the whole term circled in red approaches the value of 1. This term, for the same reason, approaches the value of 1. So what's circled in red and green is bounded. Therefore, the limit is going to be dictated by what happens to 2x cubed over 5x cubed, which this can be simplified. X cubed over x cubed just leaves me with a 2/5. Right, so that's why in algebra, you learned that your horizontal asymptote occurs at the ratio of the leading coefficients. All right, number 1 and number 2 are done. Let's work on our third function, the second rational function. Here I have a 6th degree polynomial divided by a fourth degree polynomial. So from your days in algebra, you know that this is going to have polynomial-like behavior. In fact, a 6 degree divided by a 4 degree leaves you with a 2 degree or a quadratic. You're going to end up getting quadratic behavior. And let's show this. The limit as x goes to plus or minus infinity, x to the 6 plus 3x to the 4 minus 2x cubed over 3x to the 4 minus 12. And I bet you can guess what I'm going to do. I'm going to pull out the most powerful term. Well, hopefully I did that right. And for the exact same reason, as x gets larger and larger, as x goes to plus or minus infinity, this term is going to drop down to 0. This term is going to drop down to 0. That term is going to drop down to 0. So everything circled in red there is going to approach the value of 1, so it's bounded. The behavior of this function for large x values is going to be dictated by what happens to x to the 6 over 3x to the 4, which through simplification becomes 1/3 x squared. And what happens to 1/3 x squared? Well, we know that's concave up parabola. So this function is going to have the same end behavior as 1/3 x squared. As x goes to plus or minus infinity, so if I go in that direction, or if I go in that direction, my function is going to approach positive infinity. All right, our fourth and final function, the third rational function. So think about it. We've gone through 2 of the cases so far. The degrees have been the same. The degree has been larger on top than it was on bottom. Now it's time for the third case. What happens if I have a higher degree in the bottom than I do the top? From your days in algebra, you know that you're going to have a horizontal asymptote at 0. Let's see why. If I look at the limit as x goes to plus or minus infinity of 1 over 2x plus 3, this factors to, I want to pull out a 2x. Everything in red is bounded, right? As x gets larger and larger, that term approaches 0. So the whole term in red approaches the value of 1 over 1, or 1. So that's bounded. The behavior of this function is dependent upon what's happening to 1 over 2x. Right? Everything else. And what happens to 1 over 2x as x gets larger and larger? Well, this drops down to 0. Right? No matter if you're moving to the left or if you're moving to the right. As x values get larger and larger, that drops down to 0. So that's why you have a horizontal asymptote at 0 whenever your denominator is a higher degree than your numerator.